Good morning, students. Myself, A. Srinivas, Assistant Professor, Department of Physics, KITS Institute of Technology and Science, Warangal. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC702C. Topic: Mathematical analysis of two-cavity Klystron amplifier. Microwave tubes are constructed to overcome the limitations of conventional tubes and UHF tubes. The principle of basic operation is velocity modulation. Velocity modulation means the variation of the electron beam varies in accordance with the gap voltage. This is a schematic of two-cavity Klystron amplifier. Dear student, you're supposed to remember the positions while doing the derivation of this particular topic. This is the position of electron gun, and this is the position of gap A, and this is the drift space, and this is the position of gap P, and it is collector. The electrons are generated by the electron gun and collected across the collector. The supply voltage is given by V0. Here, electron gun is at negative potential, collector is at positive potential. Now here, after forming bunches, these bunches move in drift space, excite oscillations in the catcher cavity, and develops the output voltage. Develops the output voltage. The output voltage can be collected across the catcher cavity with the help of coaxial loop. Now here, uh, before going to the derivation, you should have the clear idea about the position. This is the position of electron gun, and this is the position of collector. It is at positive potential, it is at negative potential with respect to supply voltage. And here, this is the position of gap A, and this is the position of gap B. The electrons are generated by the electron gun moving towards the collector, and here the signal to be amplified is applied at the input cavity, that is given by some Vs is equal to V1 sine omega t. And here the value of V1 is very much greater than the supply voltage. The input signal applied excite oscillations in the buncher cavity and develops the voltage of the same frequency. And here the electron which leaves gap A at this particular instant are unaffected by the gap voltage, moves with the velocity V is equal to V0. And here the electron which leaves gap A at point C dash, which moves later than the reference electron, are called late electron, subjected to positive maximum of RF cycle, accelerated, and moves with the velocity V greater than V0. And here the electrons which leaves gap A at point A dash are affected by negative maximum of RF cycle, decelerated, moves with reduced velocity. And here these electrons form bunching. Now here, before going to the mathematical analysis, you just practice this particular diagram. Here V0 is the velocity of the electron beam before entering the buncher cavity. V1 is the velocity of the electron beam after leaving the buncher cavity. Means here the electrons are affected by gap voltage, moves with the velocity V1. Here T0 time for electron enter the buncher cavity, T1 time for electron leave the buncher cavity. Here capital L is the length of drift space. After traveling some distance in drift space, the electrons form bunches. And these bunches move towards the collector by passing through the position of gap B. Now here, after traveling some distance from the buncher grid, let it be L1 distance, the electron bunches are formed. The electron bunches are formed. Now here, equation of velocity modulation is, now here V naught is the velocity of the electron before entering the buncher cavity. Vs is the signal to be amplified, and kinetic energy of the electrons at the time of leaving the buncher cavity is given by half into mv1 square. It is the kinetic energy. And the static energy. The static energy of the electrons at the time of leaving the buncher cavity means here these are generated by electron gun and are affected by the gap voltage. So here generated by the electron gun and affected by gap voltage sine omega t. Now here we can equate the kinetic energy and static energy at the time of leaving the buncher cavity, that is given by equation number 1. And after rearranging equation number 1, we get equation number 2, that is V1 is equal to V naught of 1 plus V1 by 2 V naught sine omega t1. And this particular equation is called equation of velocity modulation. And the maximum velocity occurs at plus pi by 2. Substitute in equation number 2, we get V1 max is equal to V naught of 1 plus V1 by 2 V naught. And minimum velocity occurs at minus pi by 2. Substitute minus pi by 2 in equation number 2, we get V1 minimum, that is V naught of 1 minus V1 by 2 V naught. The next is beam coupling coefficient. The beam coupling coefficient general formula is beta is equal to sine theta g by 2 by theta g by 2. Now here, if we are supposed to determine the beam coupling coefficient at the input side, then this should be subscripted as I. And at the output side, beta naught is equal to sine theta z by 2 at the output side, by theta z by 2 at the output side, given by equation number 6. Theta z is equal to omega d by v naught, average gap transit angle. Here, small d is the gap spacing in the cavity, and if it is the buncher cavity, then it is di, and if it is catcher cavity, then it is d naught. The next is bunching parameter. Bunching parameter x is defined by beta I v1 by 2 v naught theta naught. Here beta is the beam coupling coefficient at the input side. V1 is the RMS value of the input voltage applied. V naught is the supply voltage. Theta naught is the DC transit angle, and it is given by omega L by V naught. Theta naught is equal to omega L by V naught. The next is bunching length. Here the electrons are generated by electron beam, and here the signal to be amplified will be applied at the buncher cavity. The applied signal excites oscillations in the buncher cavity. The electrons which leaves gap A at this particular instant are velocity modulated and forms bunching. After traveling some distance L1 from the buncher grid, the electron forms bunching, and these bunches moves towards the gap A, moves towards collector through gap B position. Here we are supposed to calculate the length of L1. Dear students, you refer textbook Samuel Vailiavo, page number 348. The length of bunching L1 from the buncher grid can be calculated as V naught velocity of the electron before entering the buncher cavity, and pi V naught. V naught is the supply voltage, omega associated with frequency, V1 is the magnitude of input signal, where V1 is equal to Vs, V1 sin omega t. Once again, I will read out. L1 is equal to V naught of pi V naught by omega V1. The next is power output and efficiency. To determine the power output and efficiency, uh, you should know the equivalent circuit of catcher cavity. This is the output voltage induced in the catcher cavity. Now here, the fundamental component of induced current in the catcher cavity is given by I2, small I2 induced is equal to beta naught I2, beta naught 2I naught J1 of x e power minus j theta naught dash. Now here, while deriving power output and efficiency, you should remember this equation number 7. That is, small I2 induced is equal to beta naught I2 is equal to beta naught 2I naught J1 of x e power minus j theta naught. If it is reflex klystron, then you will get some dash here, at bunching parameter and at DC transit angle. The magnitude of the induced current is given by equation number 10. Here J1 of x is the Bessel function. The voltage at the equivalent circuit of catcher cavity, that is V2 is equal to beta naught I2 current and effective shunt resistance and the AC power output. We know the formula I square by 2 into RSH. And for DC, it is DC is equal to I naught V naught. I naught is the input current, V naught is the DC voltage. Now here the efficiency is equal to P out by P in by substituting equation number 12 and 14 in 15, and after rearranging you will get the equation for efficiency eta is equal to beta naught J1 of x V2 by V naught. And here, to determine the theoretical maximum efficiency of reflex klystron, we have to consider the maximum values of these parameters associated with equation number 16. That is, eta max is equal to beta naught max, J1 of x max, V2 by V naught max, and it is equivalent to 58.2%. This can be calculated by considering the Bessel function J1 of x max is equal to 0.582. It is predefined, and in critical case, V2 by V naught max is approximately equal to 1, and beam coupling coefficient at the output side is beta naught max is equal to 1. By considering all these things, we get the theoretical maximum efficiency of two cavity Klystron amplifier as 58.2%. The practical efficiency is definitely less than 58.2%. Thank you. We will meet with the next lecture. అయిపోయింది ఇది ఎంత వచ్చిందో 4